Hello, and welcome to this second video on stoichiometry, where we're going to discuss volume and mass conversions. So in order to talk about volume and mass conversions, we actually have to do some work around gas stoichiometry. And so we know with gases have some things that we're going to study a little bit more in depth later on, but for right now, we're going to focus on any gas that's at standard temperature and pressure. And so a lot of times students are like, well, what is this? You don't really need to know for right now to do the calculations, but standard temperature and pressure, standard temperature is 273 Kelvin, which is 0 Celsius, and then standard pressure is 1 atmosphere. And so that's what STP stands for, standard temperature and pressure. And we're going to be doing some calculations where we are under standard temperature and pressure, and we are also going to assume ideal gas behavior, which is not always the case, but we're going to make that wild assumption for now in order to do these gas stoichiometry problems. And so at STP, we know that there are always 22.4 liters of gas for every 1 mole of a gas. And that's an ideal gas, okay? If it's not an ideal gas, it'll derivate from there. And honestly, at this point in your chemistry career, you just don't need to know about that quite yet. So we're going to take a look again at the stoichiometry organizer that we've been using, and we're going to focus on the right-hand side for right now where we see volume. Okay, and remember, A is what you are given in the problem, and B is what you're trying to solve for. And the new step that we have from earlier when we did our mole conversions is this mole ratio step where we're using our balanced chemical equation to do a mole ratio. And so we're going to go, in our first one, we're going to go from volume of A to volume of B, and it's a 3-step process, and I'm going to show you hopefully a way that you can shorten that up if you do a problem like this. And so let's go ahead and take a look at our first problem here. In our first problem, it says how many liters of O2 were combusted if 12.6 liters of H2 were produced at STP. And we're going to assume these are gases for now. Okay, so we're going to make that assumption that these are gases. And so we are going from liters of A. Okay, so this is A. We are going to assume this is a gas. And we want to know liters of B. So oxygen is going to be our B. All right, so let's go ahead and set up our process. So we have 12.6 liters of H2O. For 1 mole of any gas, there are 22.4 liters. So for H2O, we'll make that assumption. Might be a big assumption for H2O water vapor. For every 1 mole of H2O. Okay. Our mole ratio step, we are going to use 4 moles of H2O for every 5 moles of O2 from our balanced chemical equation. And then finally, we want to get into liters of O2. So for every 1 mole of O2, there are 22.4 liters of O2. Now, you could multiply across the top and across the bottom, and then divide top by bottom. But I want to show you a couple things here to take a look at. So the first thing, I'm going to just go ahead and double check that my liters of H2O cancel, my moles of H2O cancel, my moles of O2 cancel, and I'm left with liters of O2, which is what I wanted to know. Now, I want to also show you that we have 22.4 liters and 22.4 liters. That actually can cancel as well. And so honestly, when you do these calculations, you can just use the mole ratio if you want to, because that 22.4 ends up getting canceled out. So you can do the whole math if you want to, or you can cancel those out and just use the mole ratio. If you're going from volume of one thing to volume of another, you can just use this mole ratio right here. Okay, either way will work. You will get the correct answer. And so my answer for this one is going to be 15.8 liters of O2. Okay, so that's what we end up getting. All right, so let's go ahead and take a look at some examples that we don't go from volume of A to volume of B, but maybe we're going to mix it up a little bit. So in the next one, skip past our organizer really quick and we'll go back to it. What mass of C3H8 was combusted if 29.4 liters of CO2 were produced? Okay, so we can go between any of these. It doesn't matter which one's products or reactants at this point. And so we see that we had carbon dioxide that was produced. Okay, and we're starting with that. So that's going to be our A. Even though it was the product, it's what we're given in the problem. So that's our A. And then we want to know the mass of that propane. So we want to know this. All right, let's go back to our organizer. So we are going to start with volume of A. We were given a volume of A. We're going to go to moles of A, then to moles of B using that mole ratio, and then we're going to go to the mass of B. So we are going to go from volume to mass. So let's go ahead and do that. All right, we're going to start with our 29.4 liters, 29.4 liters of CO2. We have 22.4 liters of CO2 for every 1 mole of CO2. All right, mole ratio, 3 moles of CO2 for 1 mole of C3H8. So we're going to do 3 moles of CO2 to cancel the moles of CO2 on the top for 1 mole of C3H8. Okay. And then finally we want to use our molar mass of C3H8. And we've already calculated this before, and it's 44 grams per mole. So for every 1 mole of C3H8, we have 44 grams of C3H8. Okay, let's double check that our stuff is canceling properly. So liters of CO2 cancel, moles of CO2 cancel, moles of C3H8 cancel, and we're left with grams, which is what we want to know. And so when we calculate this out, we should get 19.3 grams. Okay, so 19.3 grams of C3H8. Okay. Let's try one more problem here, just to do an extra one for practice here. So how many liters? We want to know liters of O2, so that's going to be our B, were combusted to produce 78.3 grams of CO2. So 78.3 grams, that's going to be our A. So now we're starting with mass of A. Let's go back. We're going to start with mass of A in this one, because that's the value that's given to us in the problem. And we are going to go until we get to volume of B. We want to know a volume of O2. All right, let's go ahead and do this. So we're going to start off with 78.3 grams of CO2. Okay. Molar mass for CO2 is the same as C3H8. They're both 44 grams per mole, so we're going to go ahead and do 44 grams of CO2 per 1 mole. That's why you're seeing 44 grams often, because they both have the same molar mass. Just happened to happen that way. Coincidence. Okay. And so now let's go ahead and use our mole ratio to go from moles of CO2 to moles of O2. So for every 3 moles of CO2, we have 5 moles of O2. All right. And then our final step, we want to get into liters of O2. So for every 1 mole of O2, there are 22.4 liters of O2 at standard temperature and pressure. Now, if we aren't at standard temperature and pressure, we do some different calculations, but we are not going to do that quite yet. All right, let's check our our units. So grams of CO2 are canceled, moles of CO2 cancel, moles of O2 cancel. I'm left with liters, so that's a volume for O2, which is perfect. And when I calculated that out, I got 66.4 liters of O2. And I hope that helps you out. We will take a look at some more examples of these in class.